Imagine a world not too different from our own blue planet, where the vast, life-giving oceans, those magnificent cradles of all existence, didn't just recede or freeze, but completely vanished. Picture them not merely evaporating slowly, but boiling away in a cataclysmic hiss, leaving behind nothing but parched, desolate basins stretching for thousands of miles, glimmering with the ghost of water that once was. This isn't some far-fetched science fiction plot conjured for a blockbuster movie, and it's not a nightmarish vision of an alien world. This is a chilling, yet incredibly compelling, hypothesis about Earth's own ancient past, one that whispers from the deepest recesses of geological time. Welcome, truth seekers and curious minds, to a journey into a mystery shrouded in eons, the ocean that boiled away evidence of Earth's most extreme superheating event. Today, we're not just observing, we're delving deep into the very heart of our planet's history, chasing the faint yet undeniable geological echoes of a time when our home endured an unparalleled thermal assault. It's a mystery so profound, so utterly transformative, that it's etched deep within the rock record, patiently waiting for us to decipher its secrets. This isn't just another historical curiosity, a dusty academic pursuit confined to the halls of geology departments. Far from it. Understanding such extreme planetary events, the very boundaries of what our world can withstand, fundamentally reshapes our perception of planetary resilience and, more importantly, the exquisitely delicate balance that has sustained life here for billions of years. It forces us to confront the profound fragility of our present climate, making the modern environmental challenges we face today feel both small in comparison, yet infinitely more urgent. Prepare yourselves, because what we're about to uncover will challenge your assumptions about Earth's steadfast nature. We'll be piecing together astonishing evidence gleaned from ancient zircons, isotopic signatures, and cryptic geochemical anomalies, all pointing to a period where our planet flirted with total desiccation. We'll explore the scientific debates, the competing hypotheses, and the cutting-edge technologies that are finally allowing us to peer through the mists of time. This is more than just a story of geological forces. It's a saga of extremes, of survival, and of the incredible, almost miraculous, re-emergence of liquid water on a world that may have once lost it all. Join us now as we confront the implications of a truly unimaginable planetary catastrophe, and perhaps glimpse a future our planet might have otherwise taken. Our first breathtaking mystery unfolds not with a bang, but with a fundamental question that has puzzled scientists for decades. How did Earth, emerging from the fiery chaos of a hot, volatile protoplanetary disk, manage to hold onto enough water to even begin forming those magnificent oceans in the first place? Think about it. Our planet coalesced from a swirling cloud of gas and dust, a process that would have generated immense heat, easily vaporizing any primordial water. Yet here we are, the blue planet covered in liquid. This isn't just a simple query. It's a profound paradox that sets the stage for understanding any potential loss of that water later on. One dominant theory points to a cosmic delivery service, comets and asteroids. These icy wanderers, rich in water and other volatile compounds, are believed to have bombarded the early Earth long after its initial formation. Imagine a relentless cosmic hailstorm, not of ice cubes, but of vast, dirty snowballs, each impact adding to Earth's growing water budget. This idea is supported by the fact that many meteorites, remnants from the early solar system, contain water locked within their mineral structures. Analyzing the chemical fingerprints of this extraterrestrial water, particularly its isotopic ratios, provides crucial clues. For instance, the ratio of deuterium, a heavier isotope of hydrogen, to regular hydrogen in Earth's oceans can be compared to the ratios found in different types of comets and asteroids. This comparison acts like a cosmic detective's tool, helping us trace the likely origins of our planet's water. If our water came primarily from specific types of comets, their isotopic signature should match. Another compelling hypothesis suggests that Earth's water wasn't just delivered from space but was in part intrinsic to its formation. As the planet accreted, it incorporated hydrated minerals, rocks that naturally contain water molecules within their crystal structures. These minerals, formed further out in the colder regions of the protoplanetary disk, would have been drawn inward, bringing their water content with them. As Earth grew and heated up, this built-in water would have been gradually released from the minerals, eventually making its way to the surface to form oceans. This internal source, combined with the continuous delivery from impacts, paints a more complete picture of our planet's watery genesis. Understanding this dual origin is key because it highlights just how much water was available in the first place and how resilient the process of ocean formation truly was. It underscores that for an ocean to boil away, an extraordinary amount of energy would have been required to overcome eons of water accumulation. This foundational knowledge of water's deep roots in our planet's very beginnings is absolutely central before we can even begin to contemplate the possibility of its complete disappearance. Given the extraordinary amount of water that fundamentally became part of our planet, the second deep mystery we face asks whether Earth's early, violent history could have contributed to an extreme superheating event. Before complex life truly took hold, our young planet endured a period of intense asteroid and comet impacts, a tumultuous era known as the Late Heavy Bombardment. Imagine a relentless cosmic shooting gallery, with massive celestial bodies constantly slamming into Earth between approximately 4 billion and 3.8 billion years ago. Could the immense energy released during this period, combined with the planet's already scorching internal heat, have been enough to trigger or significantly contribute to an ocean boiling catastrophe? To grasp the scale of these impacts, let's consider that the bodies hitting Earth during the Late Heavy Bombardment were not mere pebbles. They were often hundreds of kilometers across, some even reaching the size of small planets. Each collision would have released kinetic energy equivalent to billions of atomic bombs, instantly vaporizing rock and water and sending immense shock waves across the globe. For a young, still-forming planet, these impacts weren't just surface disruptions. They were fundamental shakers of its very structure. The sheer thermal consequences of such impacts are almost beyond comprehension. We're talking about a planet that was already incredibly hot from its accretion process, still differentiating its core and mantle, emitting tremendous internal heat. Add to this the external furnace of continuous cataclysmic impacts. The immediate effect of these massive collisions would certainly have created localized, boiling zones where vast quantities of water would have flashed into steam, probably creating temporary steam atmospheres. But the question is whether the cumulative effect, the relentless barrage over millions of years, could have led to something far more extensive, a global superheating event that threatened all of Earth's nascent oceans. Researchers model these scenarios, trying to understand how the energy from these impacts would have dissipated. Would it have been absorbed by the crust and mantle, leading to widespread melting? Or would a significant portion have radiated back into space, or, more ominously, been trapped by an increasingly dense steam atmosphere, leading to a runaway greenhouse effect? The challenge lies in understanding the interplay between external impacts and internal heat. The impactors themselves would have delivered more heat, but also potentially more volatile materials. The sheer volume of incoming material could have driven widespread volcanism, further venting heat and gases into the atmosphere. This period was not just about the delivery of water, but also about its potential destruction. The forces at play were so extreme that even if our planet somehow began with ample water, the energy of the late heavy bombardment presents a formidable challenge to its continued liquid existence. The scars of these impacts are still visible on the Moon, a silent testament to the violence Earth also endured, forcing us to consider how our planet survived, or perhaps even temporarily succumbed, to such an inferno. Even if Earth somehow survived the late heavy bombardment with its oceans intact, another profound puzzle emerges when we look at the Sun itself. This brings us to our third great mystery, the faint young sun paradox and the critical role of early Earth's atmospheric composition. Geological evidence, like ancient pillow lavas and sedimentary rocks, clearly indicates that liquid water was present on Earth as far back as 3.8 billion years ago, forming oceans, lakes, and rivers. But here's the paradox: during that period, our Sun was significantly dimmer, radiating only about 70% of the energy it does today. If Earth relied solely on this reduced solar output, our planet should have been a frozen wasteland, locked in a perpetual ice age. So how could liquid water possibly have existed, let alone thrived, on a planet illuminated by such a faint sun? The most compelling explanation for this apparent contradiction points directly to the necessity of a potent greenhouse atmosphere. This wasn't the kind of atmosphere we breathe today, rich in nitrogen and oxygen. Early Earth's atmosphere was likely dominated by gases with powerful heat-trapping capabilities, far more efficient than modern carbon dioxide. Imagine a thick, insulating blanket wrapped around the planet, keeping it warm despite the sun's weak glow. Key players in this ancient greenhouse effect would have included vast quantities of carbon dioxide, released by intense volcanic activity, and possibly much higher concentrations of methane, a gas with an even stronger warming potential, potentially produced by early microbial life. Water vapor itself, while crucial for liquid oceans, also acts as a powerful greenhouse gas, creating a complex feedback loop. Understanding the atmospheric components and their roles in trapping heat is vital, because any shift in this delicate composition could have had catastrophic consequences. While these gases were essential for keeping the early Earth warm enough for liquid water, their abundance also created a precarious balance, a climate system perched on a knife edge. A sudden, massive release of even more greenhouse gases, perhaps from supervolcanic eruptions far beyond anything we see today, or the widespread melting of frozen methane deposits known as clathrates, could have pushed the planet beyond a critical threshold. This tipping point is known as a runaway greenhouse effect, a scenario where rising temperatures cause more water to evaporate, which in turn traps even more heat, leading to further evaporation, in a vicious cycle that spirals out of control. If this runaway effect were to take hold, it wouldn't just make Earth uncomfortable, it would lead to extreme heating capable of boiling away entire oceans. The liquid water would vaporize, becoming part of the superheated atmosphere, further intensifying the greenhouse effect until no liquid water remained on the surface. The atmospheric pressure would soar, and temperatures would rise to hundreds of degrees Celsius, making the planet utterly inhospitable to anything resembling life as we know it. For scientists studying the ocean that boiled away, grasping the intricacies of early atmospheric chemistry is not just an academic exercise. It's key to understanding how Earth could have tipped towards such an extreme heating event, transforming from a watery world into a parched oven. The delicate chemical dance in our atmosphere holds the secret to our planet's past and perhaps its future. Even with a powerful greenhouse atmosphere, the Earth's early climate remained precariously balanced. This brings us to our fourth profound mystery, the terrifying potential of volcanic super-eruptions and vast mantle plumes. Imagine volcanic events so immense that they dwarf anything humanity has ever witnessed. These are known as large igneous provinces, or LIP, and they represent periods when colossal amounts of molten rock erupted onto the Earth's surface or intruded into its crust over relatively short geological timescales. These aren't your typical volcanoes spewing ash and lava for a few days or weeks. We're talking about events that could last for millions of years, covering continents in hundreds of thousands or even millions of cubic miles of volcanic material. To put that into perspective, the largest eruption in recorded human history, the Tambora eruption in 1815, created a global cooling event for several years. Now, multiply that by orders of magnitude and imagine a sustained release of heat and gases on a planetary scale. Could one or more of these LIPs, on an unprecedented scale, have triggered or exacerbated a global boiling event, sending Earth spinning into a runaway greenhouse nightmare? The geological evidence for these super-eruptions is indisputable. We find massive accumulations of igneous rock, tracing ancient lava flows and intrusions that stretch across vast regions of continents and ocean basins. For example, the Siberian traps, which erupted around 252 million years ago, are linked to the Permian Triassic extinction event, the most severe mass extinction in Earth's history, wiping out over 90% of marine species and 70% of terrestrial vertebrate species. This single LIP released enough carbon dioxide and other greenhouse gases to dramatically warm the planet, acidify the oceans, and deplete atmospheric oxygen. Now consider the early Earth, far more volcanically active due to its greater internal heat. The frequency and magnitude of LIPs during the Hadian and Archean eons would have been far beyond anything seen since. Each eruption would have injected colossal amounts of greenhouse gases, carbon dioxide, methane, sulfur dioxide, and water vapor directly into the atmosphere. The sheer volume of material released would have added immense heat energy to the surface and atmosphere, further stressing an already delicate climate system. The duration of these events is also critical. Unlike a single explosive volcanic eruption, LIPs represent prolonged periods of intense volcanic activity. This sustained outgassing could have continuously pumped greenhouse gases into the atmosphere, preventing the planet from cooling down and eventually overwhelming its natural carbon sinks, pushing it irreversibly toward a runaway greenhouse state. Analyzing the intensity and sheer volume of material released from these ancient super-eruptions allows scientists to model their potential to fundamentally alter the planet's climate. Imagine a scenario where multiple overlapping LIPs occur, or a single, extraordinarily massive one, perhaps triggered by the ascent of an exceptionally large mantle plume, a column of hot rock rising from deep within the Earth. Such an event could have released enough energy and greenhouse gases to not only warm the planet, but to initiate the positive feedback loops that lead to a boiling ocean. The heat from the lava itself, combined with the atmospheric blanketing effect of the gases, could have been the final, decisive push that sent Earth from a world with liquid oceans to a desolate, parched landscape. The scale of these events dwarfs anything human civilization has ever witnessed, and understanding their potential impact is crucial to unraveling the mystery of the ocean that boiled away. The terrifying scale of these ancient super-eruptions paints a stark picture, Yet the most compelling evidence for an ocean that truly boiled away comes not from fiery landscapes, but from something far more subtle and microscopic: the isotopic signatures etched within Earth's oldest rocks. This brings us to our fifth profound mystery: the dehydration clues hidden in these chemical fingerprints. Imagine tiny, invisible variations within the very atoms that make up a rock, variations that can speak volumes about the conditions of their formation billions of years ago. We are talking about isotopes, which are atoms of the same element that have different numbers of neutrons. While they behave chemically the same, their slight mass differences can reveal secrets about their journey through the Earth systems. Specifically, scientists hunt for telltale shifts in oxygen isotopes. Oxygen exists primarily as two stable isotopes: oxygen-16, which is lighter and more abundant, and oxygen-18, which is heavier. The ratio of these isotopes in water changes with temperature. For instance, in colder conditions, water molecules containing the heavier oxygen-18 tend to evaporate less readily. Conversely, during extreme heating events, this distinction becomes even more pronounced. If an ocean were boiling away, the process would preferentially remove the lighter oxygen-16, leaving the remaining water enriched in oxygen-18. When minerals then crystallize from or interact with this superheated, isotopically altered water, they lock in that unique signature. By analyzing these ratios in ancient cherts, gneisses, and other primeval rocks, researchers can reconstruct estimates of past oceanic temperatures and even infer the presence or absence of vast bodies of liquid water. Finding rocks with abnormally heavy oxygen isotopic compositions could be a smoking gun, indicating an environment where water was being rapidly depleted through vaporization. Beyond oxygen, hydrogen isotopes also offer crucial insights. Hydrogen has a heavier cousin called deuterium, often referred to as heavy hydrogen. The ratio of deuterium to hydrogen in water is another critical indicator, particularly when considering evaporation. Just like with oxygen isotopes, lighter hydrogen tends to evaporate more easily than deuterium. So, if an ocean experienced widespread boiling and rapid evaporation, the residual water would become progressively enriched in deuterium. Minerals forming from or interacting with this deuterium-enriched water would then preserve this unique signature. Scientists can extract water from ancient mineral inclusions or analyze the hydrogen incorporated directly into mineral structures to measure these ratios. A significant elevation in the deuterium to hydrogen ratio within rocks formed during a specific period could point directly to a large-scale desiccation event, where massive amounts of lighter water were lost to the atmosphere, leaving behind a heavy isotopic residue. The process of analyzing these microscopic indicators is painstaking. Researchers use highly sensitive instruments like mass spectrometers to precisely measure the isotopic ratios in minute rock samples, sometimes extracted from crystals no larger than a grain of sand. They must carefully consider potential contamination and secondary alterations that could have occurred over billions of years. But when the data aligns, it provides a powerful, direct window into Earth's deep past, allowing us to reconstruct ancient environmental conditions with remarkable precision. These subtle isotopic shifts are like forensic clues, piecing together the story of catastrophic water loss, providing some of the most compelling evidence that Earth's oceans might not always have been the stable, life-sustaining environment we know today. They offer a silent, chemical testament to the immense forces that have shaped our planet across eons. While isotopic signatures offer a chemical echo of a lost ocean, another fascinating and hotly debated mystery concerns the Earth's interior, the wet mantle versus dry mantle debate. Below our planet's crust lies the mantle, a vast layer of mostly solid rock that extends thousands of miles deep. For decades, scientists largely believed this mantle to be relatively dry, containing only trace amounts of water. However, more recent research, particularly over the last 2 decades, has revealed that the mantle can actually hold an astonishing amount of water, locked away within the crystal structures of high-pressure minerals like ringwoodite and wadsleyite. This isn't liquid water as we know it, but rather hydrogen and oxygen atoms incorporated into the mineral lattice, essentially making the rock hydrous. Think of the mantle as a colossal, slow-moving sponge. Estimates suggest that the amount of water stored within the Earth's mantle could be equivalent to, or even several times greater than, the total volume of all the oceans on the surface. This realization has profound implications for our understanding of Earth's deep water cycle, and crucially, for the idea of an ocean that might have boiled away from the surface. The wet mantle hypothesis posits that a superheating event on the surface could have driven immense quantities of water from the atmosphere and shallow crust deep into the mantle. Imagine the pressure and temperature conditions within the mantle. Under these extremes, water molecules don't simply condense, they become chemically bound within the minerals. If a surface ocean truly vaporized, some of that atmospheric water vapor could have later been transported downward through subduction zones, where oceanic crust plunges back into the mantle. This process would effectively pump water into the deep earth, changing the mantle's composition and potentially altering its physical properties, like viscosity and melting points. A mantle that received a sudden, massive influx of surface water would look different, geochemically speaking, from one that remained largely isolated from surface hydrological processes. Conversely, some scientists argue that if the early Earth's mantle was already wet, it could have acted as a source of water for the initial formation of oceans. This would imply an internal origin for much of Earth's water, rather than solely relying on extraterrestrial delivery from comets or asteroids. The debate itself highlights the dynamic interplay between the surface and the deep interior. If vast amounts of water were transferred between these reservoirs, what evidence would remain? Researchers are actively investigating this by studying mantle-derived rocks brought to the surface through volcanic activity, such as kimberlites and ocean island basalts. Analyzing the water content and isotopic signatures within these deep-seated rocks can provide clues about the mantle's ancient hydrological state. For example, if a specific period in Earth's history shows a significant increase in the water content of mantle-derived minerals, it could be interpreted as evidence of water being transported downwards from a once boiling surface. Furthermore, the presence and distribution of water in the mantle influence large-scale geological processes like plate tectonics and mantle plumes. A wetter mantle is generally softer and more prone to convection, potentially affecting the rate at which crust is recycled. Therefore, understanding the mantle's water content throughout Earth's history isn't just about tracing a lost ocean. It's about comprehending the fundamental processes that shape our planet's geology and climate. The mantle, far from being a static, dry interior, is a crucial player in Earth's water story, capable of absorbing or releasing colossal amounts of this life-giving substance over geological timescales, acting as an immense subterranean reservoir that might hold secrets to our planet's most extreme superheating events. If the wet mantle debate grapples with water hidden deep within our planet, our seventh mystery brings us back to the surface, searching for direct, undeniable physical evidence of a vanished ocean in primeval sediments. Imagine a scenario where a global ocean simply boiled away. What would be left behind? Not just a memory, but potentially vast parched plains scarred by the retreat of water. This is where geologists turn their gaze to ancient desiccation cracks and massive evaporite deposits. Desiccation cracks, more commonly known as mud cracks, are familiar sights in drying puddles or lake beds. As wet mud dries, it shrinks and cracks, forming a distinctive polygonal pattern. On a planetary scale, if an ocean were to vanish, the exposed seabed, once submerged, would undergo this same process but on an unimaginable canvas. We're talking about cracks stretching for miles, forming patterns visible perhaps even from space, if such a vantage point existed back then. The key isn't just finding ancient mud cracks, because those can form from local drying conditions. The crucial evidence would lie in their sheer scale, their widespread distribution across what were once ocean basins, and their association with other indicators of extreme aridity. Finding evidence of such cracks in rocks billions of years old presents a monumental challenge, as geological processes like erosion and metamorphism tend to obliterate such delicate features over vast timescales. Yet, if they exist, they would be a powerful testament to a planetary-scale drying event, far beyond what happens in a temporary drought. Even more compelling would be the presence of immense evaporite deposits. Evaporites are rocks formed from the evaporation of water, leaving behind dissolved minerals like salt halite, gypsum, and potash. Think of the vast salt flats of Death Valley or the Bonneville salt flats in Utah, but multiplied by a factor of thousands, perhaps millions. If a global ocean evaporated, it would leave behind colossal layers of these minerals, potentially hundreds or even thousands of feet thick, blanketing what were once ocean floors. These deposits aren't just remnants of water, they are direct chemical fingerprints of its disappearance. The sheer volume and purity of such ancient evaporites would distinguish them from smaller, localized salt deposits found in ancient lakebeds or restricted basins. Their stratigraphic position, lying above rocks formed in deep marine environments and below later terrestrial or shallow marine sediments, would tell a story of profound environmental shift. Scientists look for these ancient salt and gypsum layers in very old rock formations, though finding them is incredibly difficult. Over geological time, salts are highly soluble and often get dissolved away or tectonically deformed. However, if such massive formations survived, their composition could provide further clues. For example, the specific types of salts and their isotopic ratios might indicate the rate of evaporation, the chemistry of the water that evaporated, and even the temperature conditions at the time. A rapid, high-temperature evaporation event, consistent with a boiling ocean, would leave a distinct chemical signature compared to gradual desiccation over millions of years. These ancient features, whether the skeletal remains of desiccation cracks or the buried tombs of evaporated salts, whisper a stark story of vanished water, urging us to decipher the dramatic environmental shifts that shaped our world. Shifting from the physical remnants of a dried-up ocean, our eighth mystery explores a truly cataclysmic scenario, the runaway greenhouse effect, Earth's ultimate planetary tipping point. Imagine a positive feedback loop gone wild, where increasing heat causes more water to evaporate from the oceans, turning it into water vapor. This water vapor, a powerful greenhouse gas itself, then traps even more heat, which in turn causes more evaporation, and the cycle spirals out of control. This relentless progression can continue until all the liquid water on a planet's surface has boiled away, transforming oceans into a superheated, dense atmosphere of steam. It's a terrifying prospect, painting a picture of a world utterly transformed from a blue marble to a scorching, uninhabitable wasteland. To understand this phenomenon, we often look to our planetary neighbor, Venus, as a stark cautionary tale. Venus today is an inferno, with surface temperatures hot enough to melt lead and an atmosphere suffocatingly dense, composed almost entirely of carbon dioxide. Yet, scientists believe that early Venus was not so different from early Earth. It likely had oceans of liquid water and a more temperate climate. However, because Venus formed closer to the Sun, it received more solar radiation. Over geological time, a gradual increase in solar output, combined perhaps with massive volcanic outgassing of carbon dioxide, started a greenhouse effect. This warming triggered the evaporation of its surface water. As water vapor built up in the atmosphere, it trapped more heat, leading to further evaporation, until Venus's oceans completely vaporized. The water molecules then largely escaped into space, either through photodissociation by ultraviolet light, where water molecules were split into hydrogen and oxygen, and the hydrogen was lost, or through other atmospheric escape mechanisms, leaving behind the hellish landscape we see today. Venus stands as a chilling testament to the power of a runaway greenhouse effect and what can happen when a planet crosses that critical thermal threshold. Could Earth have faced a similar fate, even temporarily? While our planet is further from the Sun, the faint young sun paradox, which we discussed earlier, hints at Earth's precarious early climate balance. If early Earth had a particularly potent greenhouse atmosphere, or if a combination of extreme factors like massive volcanic super-eruptions and prolonged periods of high solar activity occurred together, it's theoretically possible that our planet could have flirted with, or even temporarily succumbed to, such a runaway event. The geological evidence for liquid water persisting throughout much of Earth's early history suggests that our planet largely avoided a full Venus-like runaway. However, the possibility remains that localized or episodic superheating events might have pushed parts of Earth's surface to the brink, perhaps creating transient steam atmospheres that later condensed back into liquid oceans as conditions cooled. The key lies in understanding the complex interplay between solar radiation, atmospheric composition, and volatile cycling that determines a planet's long-term habitability. The critical tipping point for a runaway greenhouse effect isn't just about total energy input, but also about the planet's atmospheric composition and ocean volume. Water vapor is crucial because it acts as both a cause and an effect. It's a powerful greenhouse gas that is released in greater quantities as temperatures rise. If a planet has too much water in its atmosphere, and that atmosphere gets too dense and hot, the water can simply stay in vapor form indefinitely, preventing condensation back into liquid oceans, no matter how much heat is radiated away. This is because the increasing pressure and density of the steam atmosphere block infrared radiation from escaping to space, even at higher altitudes where it would normally cool. Understanding this intricate balance is vital for interpreting the subtle clues left behind in ancient rocks. It helps us differentiate between periods of intense warming and a full-blown, irreversible planetary catastrophe. The difference between a very hot Earth with some liquid water and one where all the oceans have vaporized is profound, marking the boundary between a challenging environment for life and one where life as we know it simply cannot exist on the surface. Beyond the critical role of water vapor in runaway greenhouse scenarios, our ninth mystery turns to other formidable greenhouse gases that have profoundly shaped Earth's climate history: carbon dioxide and methane. These gases, while present in much smaller atmospheric concentrations than water vapor, possess an extraordinary ability to trap heat, acting like a blanket that prevents warmth from escaping back into space. Understanding their sources and sinks in the early Earth is paramount to piecing together any superheating event, as their massive releases could have been the initial spark or a significant accelerant for ocean vaporization. Consider carbon dioxide. Its primary source on a geologically active planet like Earth is volcanic activity. In the early Hadian and Archean eons, volcanic outgassing was likely far more pervasive and intense than it is today, driven by a hotter interior and more vigorous mantle convection. Imagine colossal volcanic provinces erupting for millions of years, spewing forth not just lava, but also immense quantities of carbon dioxide directly into the atmosphere. This steady or even episodic influx of carbon dioxide would have systematically ratcheted up surface temperatures. On a world already grappling with a fainter sun, a robust carbon dioxide-rich atmosphere would have been essential to maintain liquid water. But too much of a good thing can lead to catastrophe. If volcanic emissions of carbon dioxide became extreme, perhaps due to multiple super-eruptions occurring simultaneously or in rapid succession, it could have pushed the planet's thermal budget past a critical threshold, triggering the initial warming that then allowed water vapor to take over. Methane, while chemically distinct from carbon dioxide, is an even more potent greenhouse gas over shorter timescales. It traps far more heat per molecule than carbon dioxide, though it eventually breaks down in the atmosphere. On early Earth, methane could have been generated by various processes. Anaerobic microbes, ancient ancestors of today's methanogens, thrived in oxygen-poor environments and produced methane as a byproduct of their metabolism. Another significant source could have been methane clathrates, also known as methane hydrates. These are ice-like crystalline solids formed from water and methane, found abundantly in permafrost and beneath the seafloor. If global temperatures rose for any reason, perhaps initiated by volcanic carbon dioxide, these methane clathrates could have destabilized. The dissociation of these clathrates would release vast quantities of methane into the atmosphere in a relatively short period, creating a powerful positive feedback loop. A small temperature increase could release methane, which causes more warming, which in turn releases even more methane, driving temperatures even higher. This creates a terrifying amplification effect, potentially pushing the climate system into a runaway state with frightening speed. The interactions between these gases are incredibly complex and can lead to powerful amplification effects. For instance, if carbon dioxide-driven warming melted ice sheets, it could expose vast methane clathrate deposits, leading to a sudden surge in methane. This combined greenhouse effect could then push the planet into a realm where water vapor itself starts to dominate the warming, culminating in ocean vaporization. Conversely, the absence of an oxygen-rich atmosphere in early Earth meant that methane would have persisted longer, enhancing its warming potential significantly compared to today. The delicate dance between these major greenhouse gases, how much of each was present, how they were released, and how quickly they were removed from the atmosphere, is a central piece of the puzzle in understanding any past superheating events. It's a compelling reminder that Earth's climate is a system of interconnected variables where a shift in one component can trigger a cascade of dramatic consequences. Beyond the profound influences of carbon dioxide and methane, another critical piece of the puzzle in understanding Earth's deep past and potentially a superheating event lies hidden within tiny, seemingly unassuming mineral grains, zircon crystals. Imagine these microscopic geological survivors as perfect time capsules, each one holding a chemical fingerprint of the conditions on Earth when it first formed, preserving snapshots of our planet's earliest environment, including crucial evidence about the presence or absence of ancient water. These crystals are incredibly resilient, able to withstand billions of years of intense heat, pressure, and geological upheaval, making them invaluable messengers from the Hadian and early Archean eons. Their durability is truly astonishing, allowing them to outlast nearly every other component of the rocks in which they formed. scientists have learned how to unlock the secrets held within these ancient zircons by analyzing their oxygen isotope ratios. Oxygen, as you may know, comes in slightly different forms or isotopes, depending on the number of neutrons in its nucleus. The two most common stable isotopes are oxygen-16 and oxygen-18. The ratio of these isotopes within a zircon crystal is directly influenced by the temperature and the composition of the water present when that crystal first crystallized from molten rock. If a zircon forms in the presence of liquid water, especially from weathered continental crust that has interacted with oceans or surface water, it will tend to incorporate a higher proportion of oxygen-18 compared to a zircon that forms in a completely dry, molten environment. This subtle but measurable difference in isotopic composition acts as a highly sensitive thermometer and a powerful indicator of past hydrological conditions. So, when researchers discover zircons from, say, 4.4 billion years ago, and those zircons exhibit oxygen isotope ratios consistent with formation in the presence of liquid water, it provides compelling evidence that water was indeed present on Earth's surface at that incredibly early date. These findings directly challenge earlier assumptions that the Hadian eon was an entirely molten, waterless hellscape. By meticulously analyzing hundreds, even thousands of these ancient zircon grains, scientists can reconstruct a timeline of water's presence on Earth. If, for instance, a significant portion of zircons from a particular period suddenly showed isotopic signatures indicating a prolonged absence of liquid water, it would strongly support the hypothesis of a planet-wide desiccation event, perhaps even the boiling away of its oceans. These tiny, durable crystals truly hold secrets spanning eons, offering us a direct, unvarnished look into the conditions of primeval Earth. But this brings us to one of the most profound and puzzling mysteries of all. If such an unthinkable event, a superheating so intense it could vaporize oceans, truly occurred, then how did life, even microbial life, manage to survive such an ordeal, or did it completely restart from scratch? This question cuts to the heart of biology's resilience and our understanding of Earth's earliest biosphere. We know from the fossil record and genetic studies that life was already present on Earth at least 3.8 billion years ago, and possibly much earlier. If the oceans were truly gone, even temporarily, the implications for these nascent life forms are staggering. Where did they go? How did they endure temperatures that would incinerate almost any organism we know today? This is where the concept of extremophiles becomes incredibly relevant. These are organisms, predominantly microbes, that thrive in environments once thought to be completely inhospitable to life. Think of the bacteria that flourish in superheated hydrothermal vents at the bottom of the ocean, the archaea that live in highly acidic hot springs, or the microbes that survive deep within the Earth's crust, miles away from sunlight. These remarkable forms of life offer a blueprint for how life might have persisted through a global superheating event. Life could have retreated to subterranean refugia, finding sanctuary in deep rock fractures where liquid water, heated by internal Earth processes, might still have been present. Imagine vast networks of underground caves or porous rock formations, insulated from the surface inferno, providing a last bastion for life. Another possibility lies in the very deep ocean, specifically around hydrothermal vents. These volcanic openings on the seafloor spew out superheated, mineral-rich water, creating unique ecosystems completely independent of sunlight. Life around these vents is already adapted to extreme temperatures, pressures, and chemical environments. If parts of the ocean floor remained intact and geologically active, these vent systems could have served as lifeboats, protecting microbial communities from the surface catastrophe. Even if the bulk of the surface ocean boiled away, pockets of water heated geothermally or shielded by kilometers of rock might have allowed these resilient organisms to cling on, waiting for conditions to improve. The very existence of life after such an event implies an almost unfathomable degree of adaptability, pushing the boundaries of what we consider habitable. It poses profound questions about life's ultimate limits and its capacity to rebound from seemingly insurmountable planetary catastrophes. Did the few survivors then reseed the entire planet once the oceans returned, diversifying rapidly into new ecological niches? Or if life was completely extinguished, did it somehow re-emerge from non-living matter, a spontaneous genesis occurring once more in the newly reformed cooler oceans? This would challenge our current understanding of abiogenesis, the process by which life arises from non-living matter, suggesting it might be a more common or less improbable event than generally assumed. The resilience of microbial life found today, such as certain types of bacteria and archaea that can withstand radiation, extreme cold, intense pressure, and searing heat, offers tantalizing clues. These organisms, often referred to as living fossils in their tolerance of extreme conditions, might carry genetic signatures or metabolic pathways that echo the survival strategies employed by their ancient ancestors. Studying their biochemistry and environmental tolerances can provide empirical data to model how life could have survived a planetary inferno. Understanding how life might have endured such a global sterilization event doesn't just shed light on Earth's past. It also informs our search for life on other planets, hinting that life might persist in far more extreme conditions than we currently realize. Beyond the subtle shifts in isotopic ratios, which offer their own powerful insights, another layer of evidence for ancient catastrophic events lies hidden within the precise elemental composition of Earth's most ancient sediments. Think of these sediments as vast, silent libraries, each grain of sand or particle of clay a tiny archive holding information about the environment in which it formed. When scientists analyze these primeval layers, they're not just looking for evidence of water, but also for the specific elemental fingerprints that indicate radical changes in the ocean's chemistry, temperature, or even its very presence. Consider elements like sulfur and iron. Their behavior in geological systems is highly sensitive to the presence of water, particularly oxygenated water, and to temperature. For instance, the forms that sulfur takes in minerals, whether it's locked up in iron sulfides like pyrite or exists as sulfates, can reveal a great deal about the availability of oxygen in ancient oceans. If an ocean were to boil away, the sudden increase in temperature and the subsequent exposure of previously submerged sediments to the atmosphere would drastically alter the geochemistry of these elements. We might expect to find unusual concentrations or unique mineral forms of sulfur and iron that deviate wildly from what's typical in marine sediments, signaling an environment profoundly different from a stable, liquid ocean. These are not merely minor fluctuations but significant anomalies, almost like a blaring alarm in the quiet geological record. Similarly, the distribution of various trace metals within ancient sediments offers another set of cryptic messages. Elements like manganese, uranium, and even certain rare earth elements are often soluble in water under specific conditions, but they precipitate out of solution under others. Imagine what would happen if a vast ocean slowly evaporated or catastrophically boiled away. The concentration of dissolved minerals would dramatically increase, forcing many of these trace metals to precipitate out of solution in unusual ways, forming distinct layers or nodules that defy conventional explanation. Researchers look for these unexpected patterns or enrichments that don't fit the standard geological models for ocean formation, viewing them as potential markers of extreme desiccation events. They are the chemical signatures of a planet under immense thermal stress, a record of elements reacting to an environment fundamentally altered by the absence of their primary medium. Detecting these anomalies requires meticulous analysis using advanced geochemical techniques, often involving dissolving microscopic samples of rock and running them through sophisticated instruments that can measure elemental concentrations down to parts per billion. The data points aren't always immediately obvious, but when patterns emerge across geographically distant sites of similar age, they begin to tell a compelling story. These elemental fingerprints are not just indicators of a change in water volume. They reflect a complete reordering of the geochemical cycles that govern our planet, indicating an event so profound it left an indelible mark on the very composition of the Earth's crust. It's like finding a strange, alien message etched into the bedrock, a testament to a planetary history far more turbulent than we often envision. Beyond these telling elemental fingerprints, we must now turn our gaze to Earth's earliest infancy, an epoch so extreme it was named the Hadian after Hades, the Greek god of the underworld. Imagine a time when our planet truly resembled a hellscape, a surface molten from the heat of its formation, constantly bombarded by colossal asteroids, and utterly inhospitable by any modern standard. This Hadian eon, spanning from Earth's birth 4.5 billion years ago to about 4 billion years ago, isn't just a brief, chaotic prelude to a more stable Earth. Increasingly, scientists are asking if the ocean that boiled away wasn't a singular, isolated catastrophe much later in Earth's history, but rather a characteristic defining feature of this primordial phase. The prevailing models for the Hadian eon often depict a very different Earth from the one we know today. After the intense heat of accretion and the moon-forming impact, the planet would have been shrouded in a thick, dense atmosphere composed largely of superheated steam, carbon dioxide, and other volcanic gases, far removed from the nitrogen-oxygen mix we breathe now. As the Earth began to cool, this steam-rich atmosphere would eventually condense, leading to the formation of the first oceans. But if cooling was interrupted by persistent superheating, perhaps from ongoing volcanic activity on a scale we can barely imagine, or continuous, massive impacts, those initial oceans might have been ephemeral, repeatedly boiling off into the atmosphere. This wasn't merely surface water evaporating. We're talking about vast volumes of water flashing into steam, creating a massive, hot, humid atmosphere that prevented subsequent condensation, essentially trapping vast quantities of H2O in a gaseous state. Consider the feedback loops at play during such a period of persistent superheating. A surface continually releasing volcanic gases, combined with a steam-rich atmosphere acting as a powerful greenhouse blanket, would effectively prevent the planet from cooling down sufficiently for stable, liquid oceans to persist. Any water that did condense would swiftly be reheated and re-vaporized. This constant cycle of vaporization and condensation, driven by extreme internal and external heat sources, would have fundamentally shaped the planet's initial crust and atmosphere. It could explain why the earliest rock record is so sparse and why the planet took so long to develop stable continental landmasses and persistent bodies of liquid water. The very formation of the first continents, for instance, might have been influenced by the intense hydrothermal alteration caused by superheated steam interacting with newly formed crust, leading to unique mineral assemblages that are rare today. This early, violent epoch holds many unanswered questions about Earth's true beginnings, challenging our assumptions about the conditions under which life eventually emerged. If the Hadian was characterized by repeated or even continuous episodes of ocean vaporization, it completely reshapes our understanding of the planet's early habitability. It suggests that life, if it arose during this time, would have had to do so under conditions of unimaginable thermal stress, perhaps in deep-sea hydrothermal vents shielded from the surface chaos, or in transient, highly acidic pools that formed during brief periods of surface stability. The very concept of stable oceans might be a relatively recent phenomenon in Earth's deep history, making the Hadian Eon not just a fiery hellscape, but a critical crucible where the planet's fundamental characteristics were forged under the most extreme conditions imaginable. While the Hadian Eon presents a compelling case for a persistently parched Earth, the narrative of our planet's early superheating isn't solely confined to gradual, long-term processes. Instead, we must also consider the sudden, catastrophic role of impact events. Even after the Hadian hypothetically settled into a more stable state with nascent oceans, massive asteroid and comet impacts could have, at various points in Earth's deep history, caused localized boiling or even temporarily created a global steam atmosphere, fundamentally altering surface conditions. Think of it this way: a truly immense impactor miles across, slamming into an early ocean, would generate an explosion of unfathomable power. The sheer kinetic energy would instantaneously vaporize colossal volumes of water, blasting it high into the atmosphere. This wouldn't be a slow evaporation. It would be an explosive flash boiling event, creating a transient, superheated steam atmosphere that could envelop the entire planet for a time. The immediate aftermath would likely involve widespread torrential rains of superheated water, as the steam eventually cooled and condensed, followed by a period of sustained high temperatures due to the greenhouse effect of the remaining atmospheric water vapor. But how do we differentiate between such transient, impact-induced steam atmospheres and the kind of sustained, complete ocean vaporization we've been discussing, where the oceans essentially vanish for extended geological periods? The geological markers are key. A temporary steam atmosphere, while devastating, would leave behind evidence of rapid cooling and subsequent re-establishment of liquid water. This might manifest as distinct layers of impact ejecta, followed by sedimentary structures indicative of freshwater or shallow marine environments that quickly reformed. We might find evidence of widespread alteration of surface rocks due to hot water interacting with them, but without the prolonged desiccation signatures of massive evaporite deposits or deep, persistent desiccation cracks that would indicate a truly vanished ocean. In contrast, a sustained, complete ocean vaporization event, whether driven by persistent volcanic activity or a runaway greenhouse effect, would leave a far more profound and continuous mark. Such an event would imply many millions of years, perhaps even hundreds of millions of years, without liquid surface water. The geological record from such a period would ideally show a complete absence of marine sediments, replaced instead by vast expanses of subaerial deposits, wind-blown sands, massive lava flows, or highly altered continental crust lacking any interaction with significant bodies of water. The chemical and isotopic signatures in rocks would also reflect this prolonged aridity, showing shifts that can't be explained by a mere transient heating. The sheer energy of even a single large impact is almost unfathomable, delivering the equivalent of many thousands of nuclear bombs. While terrifying, these events are generally theorized to be transient episodes, albeit ones that could trigger significant biosphere disruptions and massive climate shifts. However, for a scenario where the ocean genuinely boiled away and stayed away for millions of years, the energy source would need to be sustained, pervasive, and far more fundamental than even the most colossal single impact, pointing to deeper, planetary-scale processes that fundamentally altered Earth's thermal equilibrium. Understanding this distinction is crucial for interpreting the sparse and often ambiguous geological record from Earth's deep past. While we ponder the immediate, cataclysmic effects of impacts, another profound mystery arises: the Great Oxidation Event and its potential connection to Earth's superheating past. Imagine a world devoid of breathable air, where the atmosphere was a toxic soup of methane and carbon dioxide. Then, around 2.4 billion years ago, something truly revolutionary happened. Oxygen began to accumulate in the atmosphere, slowly but fundamentally transforming the planet. This wasn't a gradual shift, but a monumental turning point, aptly named the Great Oxidation Event. It paved the way for complex life as we know it, but what if a prior superheating event, even one that boiled away the oceans, played an unexpected role in setting the stage for this dramatic oxygenation? Consider the immense changes that a planetary desiccation event would inflict. If the oceans vanished, vast quantities of highly reactive elements, previously dissolved in seawater or bound in ocean floor sediments, would be exposed to the atmosphere. Picture immense salt flats, iron-rich deposits, and sulfurous minerals all laid bare. Normally, these elements would readily react with any nascent oxygen produced by early microbial life, effectively scavenging it before it could build up in the atmosphere. It's like trying to fill a bucket with a hole in it. Any oxygen produced would be immediately consumed by these hungry, reactive substances. But what if a superheating event, by boiling away the oceans, also drove these reactive elements deep into the Earth's crust or altered their chemical state, making them less available to absorb free oxygen? This is the intriguing hypothesis. Such a catastrophe could have effectively reset the planet's atmospheric chemistry. By stripping away these oxygen-consuming sinks, a superheating event might have inadvertently created an environment where the oxygen produced by early life, primarily cyanobacteria through photosynthesis, could finally accumulate. It's a counterintuitive thought, a devastating planetary purge creating the conditions necessary for life's next great evolutionary leap. The linkages here are complex and still hotly debated. Scientists are exploring whether the massive outgassing of gases during a superheating event could have influenced the balance of carbon and sulfur cycles, further affecting the planet's capacity to store or release oxygen. For example, if large amounts of carbon were buried deep within the Earth during or after such an event, it would leave behind more free oxygen. Similarly, changes in the availability of iron, a crucial nutrient for many early microbes, could have impacted the rate of photosynthesis itself. This potential connection between a planetary desiccation and the Great Oxidation Event is more than just a fascinating academic puzzle. It underscores the incredible interconnectedness of Earth's systems and the profound, often unexpected, ways in which major geological catastrophes can shape the biosphere. It suggests that what appears to be an unmitigated disaster could, in the long arc of planetary evolution, be a critical, albeit brutal, step towards greater complexity and diversity of life. The very act of boiling away the ocean might have been a necessary, if terrifying, precursor for the aerobic world we inhabit today, forcing a dramatic reordering of Earth's elemental cycles that ultimately allowed oxygen to reign. Having considered how a past superheating event might paradoxically pave the way for oxygen, let us now turn our attention to another of Earth's dramatic climate extremes, one that often stands in stark contrast to the idea of a boiling ocean: the Snowball Earth periods. Imagine our entire planet from pole to pole, encased in a thick shell of ice, even at the equator. This wasn't just a harsh winter, it was a global deep freeze, a planetary state that Earth has entered at least twice and possibly more times during its long history. The most recognized of these glaciations occurred around 700 million years ago, plunging the planet into conditions that pushed life to its absolute limits. But here's the profound mystery. Could the same intricate climate mechanisms that trigger such profound, global freezing also, in a twisted, inverse fashion, contribute to a superheating event? Or, even more intriguing, could the recovery from a snowball Earth trigger conditions so extreme that they lead to an ocean boiling scenario? The Earth's climate system is not a gentle thermostat. It is a complex pendulum capable of swinging wildly between thermal extremes, sometimes with astonishing speed. Consider the feedback loops at play during a snowball Earth event. As ice sheets expand, they reflect more sunlight back into space, cooling the planet even further. This increased reflectivity, known as the ice albedo feedback, drives the planet deeper into glaciation. Once the Earth is largely frozen, volcanic activity continues to release carbon dioxide into the atmosphere. With oceans largely covered by ice, there's nowhere for this carbon dioxide to be absorbed, leading to its massive accumulation in the atmosphere over millions of years. Eventually, this trapped greenhouse gas creates a super greenhouse effect so potent that it melts the global ice sheets in a geological blink of an eye. This rapid transition from extreme cold to extreme warmth is what makes the Snowball Earth event so fascinating. Now, if such a powerful greenhouse effect could melt a planet encased in miles of ice, imagine its potential if the Earth were not frozen but already warm. What if a similar accumulation of greenhouse gases, perhaps from extraordinary volcanic outpourings or other geological processes, occurred without the preceding cold snap? Could it push the planet not just to a moderate warmth, but to an unbearable heat, a true runaway greenhouse effect where oceans begin to vaporize? The sheer scale of carbon dioxide buildup required to thaw a snowball Earth is staggering, potentially hundreds of times current atmospheric levels. Such an atmospheric composition, if sustained, could unleash unimaginable thermal consequences. The Snowball Earth rebound provides a powerful analog for understanding runaway climate scenarios. It demonstrates Earth's capacity to amplify warming trends once certain thresholds are crossed. While the initial trigger for a boiling ocean might be different, the rapid and immense release of greenhouse gases necessary to thaw a global ice sheet offers a chilling glimpse into the scale of atmospheric forcing that can drive Earth's climate to its breaking point. It forces us to consider that our planet's stability is not a given, but a delicate balance, and that the mechanisms that produce ultimate cold might, in a different context, unleash ultimate heat. The very processes that bring Earth back from total glaciation could, under slightly different conditions, catapult it into a state of extreme superheating. Crucially, the next piece of this planetary puzzle involves Earth's greatest geological engine, plate tectonics. These slow, relentless movements of our planet's outer shell are far more than just what causes earthquakes and builds mountains. They are fundamental to Earth's long-term climate stability and, perhaps most importantly for our discussion, play a pivotal role in the global water cycle, constantly shuttling water between the surface and the deep interior. But was this engine running during the period when an ocean might have boiled away? The question of when plate tectonics truly began on Earth is one of the most hotly debated topics in geology. Some scientists argue that early Earth, particularly during the Hadian and early Archean eons, operated under a different regime, perhaps characterized by a stagnant lid where the surface crust was largely immobile, or by episodic, localized resurfacing rather than global, continuous plate movement. Others contend that some form of plate tectonics, albeit perhaps different from today's, was already active quite early, potentially around 4 billion years ago. If plate tectonics was indeed active during an extreme superheating event, its role in water cycling becomes paramount. Think about how plate tectonics influences water today. At subduction zones, oceanic crust saturated with water and hydrated minerals plunges back into the mantle, effectively taking surface water deep within the planet. Conversely, volcanic activity, particularly at mid-ocean ridges and through arc volcanism, releases water and other volatiles back into the atmosphere and oceans. This continuous exchange acts as a planetary thermostat, regulating the amount of water available on the surface. If this cycle was disrupted or non-existent during a superheating event, it could have drastically altered how much water remained on the surface or how quickly recondensation could occur. Consider a scenario where plate tectonics was not yet fully established during an ocean boiling event. Without the constant recycling mechanism, water might have been more easily lost to space if the atmosphere became a steam envelope, or it might have been trapped in the mantle without subsequent release. Conversely, if early, more vigorous plate tectonics existed, it might have facilitated a faster initial removal of water from the surface into the deep earth during the heating phase, but then also potentially provided pathways for its eventual return. The presence or absence of subduction zones directly impacts how efficiently water is sequestered into the mantle, and without them, the surface would be more vulnerable to atmospheric stripping. The debate over early plate tectonics is therefore not just an academic curiosity. It's central to understanding Earth's deep water cycle and its habitability. The very movement of the continents, even if it was in a primitive form, dictates how much water is stored in the mantle versus on the surface. If Earth's crust was largely immobile, then any water driven into the mantle by extreme heat might have remained trapped, making a return to a liquid ocean state far more challenging. On the other hand, a vigorous tectonic regime could have more rapidly absorbed and then slowly outgassed water, potentially aiding in the planet's eventual recovery from desiccation. The complex interplay between a dynamic interior and the surface environment means that the story of plate tectonics is inextricably linked to the fate of Earth's water, shaping our planet's destiny and its capacity to sustain life. While our focus has been on Earth's deep past, another world in our solar system offers a powerful, tangible analogy for a planet that lost its water, Mars. This red planet, now a frigid desert, bears undeniable geological evidence of a watery past, from ancient riverbeds and lake basins to mineral deposits that could only form in the presence of liquid water. Studying Mars isn't just about exploring another planet. It's like looking into a possible future or perhaps even a past for Earth itself, providing invaluable insights into planetary desiccation and the fragile nature of habitability. What happened to Mars's once abundant water offers a stark cautionary tale. The parallels between Mars's watery decline and a potential ocean boiling event on Earth might seem distant, but the underlying physical principles of water retention and loss are universal. Scientists believe that early Mars, much like early Earth, had a thicker atmosphere and a warmer climate capable of supporting liquid water on its surface. Over billions of years, however, Mars steadily lost its atmosphere, primarily due to the stripping effects of the solar wind, unaided by a sufficiently strong global magnetic field. As the atmosphere thinned, surface pressure dropped and temperatures plummeted, forcing any remaining liquid water to either freeze or sublimate directly into the sparse atmosphere. This process highlights how crucial a protective atmosphere and magnetic field are for safeguarding a planet's water supply. One critical lesson from Mars concerns the fate of water once it enters a planet's atmosphere as vapor. On Earth, our strong gravity and powerful magnetic field largely prevent water vapor from being broken down into hydrogen and oxygen and then lost to space. But on Mars, without that robust protection, water molecules in the upper atmosphere were bombarded by ultraviolet radiation, splitting them into their constituent atoms. The lighter hydrogen atoms especially easily escaped Mars's weaker gravitational pull, drifting off into space. This continuous atmospheric escape meant a one-way ticket for Mars's water, gradually bleeding it away from the planet. This mechanism provides a chilling model for what could happen if Earth's protective mechanisms were ever compromised during an extreme heating event. Furthermore, the types of geological features observed on Mars, such as vast ancient flood channels and what appear to be evidence of standing bodies of water, give us a visual blueprint of what a desiccated world looks like on a grand scale. While Earth's hypothetical ocean boiling event would have involved far more extreme temperatures, the end result, a planet stripped of its surface water, might share some common geological signatures. For example, if Earth's oceans completely vaporized and then failed to recondense, we might expect to find evidence of massive ancient lake beds or ocean basins that are now entirely dry, much like those seen on Mars. The Martian landscape, with its dried-up river networks, serves as a powerful reminder of what happens when a planet loses its vital watery embrace, making it a critical analog for understanding the limits of planetary habitability. This brings us to a fundamental concept in astrobiology and the search for extraterrestrial life, the Goldilocks Zone. This isn't a physical place in space where Goldilocks herself lives, but rather a metaphorical term describing the orbital region around a star where a planet receives just the right amount of energy to allow liquid water to exist on its surface. Not too hot so the water boils away, and not too cold so it freezes solid. It's the sweet spot for habitability, and Earth, nestled perfectly within our Sun's Goldilocks zone, is the prime example. Our planet's long history of supporting life is inextricably linked to its persistent oceans, demonstrating the critical importance of liquid water for the emergence and sustenance of biological processes as we know them. The very definition of habitability hinges on this delicate balance, making the Goldilocks zone a cornerstone in humanity's quest to find life beyond Earth. However, the very idea of an ocean that boiled away here on Earth pushes the boundaries of this Goldilocks concept, forcing us to re-examine what we truly mean by planetary habitability. If Earth, a planet seemingly ideally placed, could have undergone such an extreme superheating event, it suggests that mere orbital distance isn't enough to guarantee long-term water stability. Internal planetary processes, intense geological activity, or even massive impact events could potentially drive a world out of its habitable state, regardless of its initial position. Our own ancient history serves as a dramatic case study, illustrating that even a Goldilocks planet can experience periods of profound environmental instability, where the line between lush life and barren desolation becomes incredibly thin. It forces us to consider the dynamic interplay of factors that truly govern a planet's ability to retain liquid water over geological timescales. This perspective profoundly influences how scientists evaluate the potential for life on distant exoplanets. When astronomers discover exoplanets, especially those within their star's Goldilocks zone, there's often immediate excitement about their potential habitability. But the Earth's potential past, particularly a scenario involving ocean vaporization, adds a layer of crucial nuance to this optimism. It tells us that simply being in the right place isn't the sole determinant. We must also consider the planet's atmospheric evolution, its internal heat budget, the presence and strength of a magnetic field, and the history of catastrophic events it may have endured. For instance, a planet that experiences a runaway greenhouse effect, similar to what may have occurred on early Earth, could quickly lose its surface water, even if it started out perfectly within its star's habitable zone. This deepens our understanding of planetary evolution and the complex dance of factors required to maintain liquid water over billions of years, refining the criteria we use in the ongoing search for alien life. The saga of Earth's possible boiling ocean expands our definition of habitability beyond simple distance, incorporating the dynamic, often violent, geological history of a world. The very presence of life, even in its most primitive forms, introduces another fascinating layer to the mystery of Earth's potential superheating event. While we often think of geological forces and celestial mechanics as the primary drivers of planetary change, even early microbes possessed the uncanny ability to significantly alter their environments through their metabolic processes. This raises a profound question. Could early life in its nascent stages have contributed to, or perhaps even mitigated, a superheating event? It's a complex interplay where biology and geology are locked in a feedback loop, suggesting that life itself may have played a paradoxical role in Earth's thermal extremes. Consider the diverse metabolisms that likely existed on early Earth. Some microbes might have produced vast quantities of methane, a potent greenhouse gas, from sources like volcanic activity or hydrothermal vents. If such methane production became widespread and sustained, it could have amplified any warming trend, pushing the planet closer to a runaway greenhouse state. Imagine colonies of archaea thriving in the early oceans, continuously exhaling methane bubbles that rose to the atmosphere, forming an insulating blanket that trapped more and more heat. This biological contribution could have been a powerful, yet unintended, accelerant in any superheating scenario, taking what might have been a severe warming trend and turning it catastrophic. The sheer volume of biological activity, even by microscopic organisms, can exert enormous influence over geological timescales. Conversely, other forms of early life could have played a mitigating role. For example, some microbes might have contributed to the weathering of rocks, a process that draws carbon dioxide out of the atmosphere and sequesters it in minerals. This natural carbon capture mechanism, if robust enough, could have acted as a thermostat, helping to cool the planet and potentially pulling it back from the brink of a superheating event. Think of early microbial mats forming on exposed landmasses, slowly but steadily breaking down silicate rocks and consuming atmospheric carbon dioxide for their growth, thus reducing the greenhouse effect. Similarly, the eventual development of oxygenic photosynthesis by early cyanobacteria fundamentally altered the atmosphere, though this occurred later in Earth's history, after the period we're discussing for the superheating event. However, it illustrates the profound capacity of life to reshape a planet's atmospheric composition and, by extension, its climate. This co-evolution of life and Earth's climate highlights the intricate feedback loops that exist between the biosphere and the geosphere. It's not just that life adapts to environmental conditions, but that life actively modifies those conditions, sometimes in ways that are self-reinforcing, leading to either stability or dramatic shifts. The very processes that allowed life to flourish could, under certain circumstances, have pushed the planet towards extreme thermal states. Understanding this dynamic is crucial because it adds a biological dimension to the purely geological and astronomical factors previously discussed. It suggests that even before complex ecosystems developed, simple life forms were powerful agents of planetary change, capable of influencing global temperatures and the fate of Earth's oceans. This biological agency means that any model of Earth's early climate history must factor in the evolving impact of its earliest inhabitants, no matter how small. Beyond life's influence on early Earth's climate, another fundamental factor often goes unexamined: the planet's very own magnetic field. This invisible shield, generated deep within Earth's molten core, silently protects our atmosphere from the relentless assault of the solar wind, a stream of charged particles constantly emanating from the sun. The question arises, could a weaker or even absent geomagnetic field in early Earth have significantly contributed to atmospheric and water loss during a hypothetical superheating event, effectively leaving our planet vulnerable to being stripped bare? This protective influence, often taken for granted, is far more critical than many realize. To understand this, we need to delve into the evolution of Earth's geodynamo, the complex process that creates our magnetic field. In its earliest days, Earth's internal heat engine was different. The core was likely hotter, and the mechanisms driving convection might have varied. Scientists are still piecing together when and how our planet developed a robust, stable magnetic field. If, for extended periods in the Hadian or early Archean eons, Earth's magnetic field was significantly weaker, intermittent, or even non-existent, the implications for our atmosphere and oceans are profound. Imagine if the tiny particles of the solar wind, traveling at hundreds of kilometers a second, were able to directly bombard the upper layers of Earth's atmosphere without deflection. They would have steadily chipped away at atmospheric gases, much like sandblasting, causing lighter elements, including hydrogen, a key component of water, to escape into space. This atmospheric stripping becomes particularly relevant when considering a superheating event. If the oceans were boiling, vast amounts of water vapor would have risen into the upper atmosphere. Water vapor, while a powerful greenhouse gas, contains hydrogen, one of the lightest elements. Without a strong magnetic field to deflect the solar wind, this newly vaporized water, broken down into its constituent hydrogen and oxygen by ultraviolet sunlight, would have been highly susceptible to being stripped away. It's a double whammy. The heat drives water into the atmosphere, and a weak magnetic field allows it to permanently escape. This could have accelerated the desiccation process, turning a temporary boiling into an irreversible loss of planetary water. The correlation between a weaker geodynamo and periods of significant planetary desiccation is a crucial area of research, particularly when comparing Earth to Mars, which lost its water largely due to a decaying magnetic field. The strength of Earth's magnetic field is not static. It fluctuates over geological timescales, even reversing its polarity many times. Periods of particularly low field strength could have acted as vulnerable windows, accelerating atmospheric erosion. Scientists study ancient rocks containing magnetic minerals to reconstruct the history of Earth's field, providing clues about its past protective capabilities. These studies hint at times when our planet's shield might have been less robust, potentially coinciding with periods of extreme environmental stress. Understanding this invisible protector's history is vital for comprehending how our planet managed to retain its atmosphere and oceans over billions of years, and how it might have succumbed to or avoided complete desiccation during extreme heating events. It truly underscores how many interconnected systems contribute to Earth's habitability. While the idea of an ocean boiling away might seem like a relic of Earth's deep, violent past, it forces us to confront a chilling question: could such a catastrophe ever befall our planet again? This isn't just a theoretical exercise, it's a critical inquiry into Earth's long-term climate projections and the ultimate fate of our precious oceans, offering a sobering perspective on humanity's role as stewards of this unique planet. The past, in its extremity, provides a stark and powerful preview of potential futures, demanding our attention and careful consideration. On one hand, the natural forces that once threatened to boil our oceans were truly immense. Runaway greenhouse effects unimaginable today, supervolcanic eruptions spewing gases for millennia, and even a dimmer sun paradoxically heating the planet through atmospheric changes. These were planetary-scale events, driven by geological and astronomical processes far beyond human control. However, our modern industrial civilization has introduced a new, unprecedented variable: the rapid and massive release of greenhouse gases into the atmosphere. We are conducting a global experiment, altering the very composition of the air in ways not seen for millions of years. While current climate models do not predict a literal boiling away of the oceans, they do project scenarios of such extreme heating that could render vast swaths of the planet uninhabitable, fundamentally altering ecosystems and human societies. It paints a picture of a future where even a partial loss of water or a significant rise in sea levels due to thermal expansion and ice melt would have catastrophic consequences for civilization. Consider the long-term outlook for our sun itself. Over billions of years, as our sun ages, it will gradually expand and become hotter, eventually evolving into a red giant. This stellar evolution will inevitably lead to a future where Earth's oceans do, in fact, boil away due to purely astronomical forces. Our distant descendants, or perhaps other intelligent life, will one day witness this ultimate desiccation, a natural end to Earth's watery era. But this far-off event doesn't diminish the urgency of our current situation. The present-day challenge lies in distinguishing between inevitable cosmic processes and the accelerated changes driven by human activity. Understanding how our planet has weathered past thermal extremes offers vital lessons in resilience and susceptibility. It highlights the delicate balance of Earth's climate system and how easily that balance can be disrupted. Looking further ahead, the interactions between Earth's internal heat, the composition of its atmosphere, and the sun's evolving energy output will continue to shape our planet's destiny. Will future geological events like renewed supervolcanic activity combine with human-induced climate change to create unprecedented warming? The possibility of cascading feedback loops, where warming triggers further warming through natural processes like the release of methane from permafrost, remains a serious concern. While the scale of ancient superheating events might seem distant and extreme, they serve as potent reminders that our planet is not static, and its future climate trajectory is subject to both profound natural forces and, increasingly, the choices we make today. The lessons from Earth's deep past are not just historical curiosities. They are urgent warnings about the fragility of our planetary environment and the critical importance of thoughtful environmental stewardship in navigating an uncertain future. Despite the compelling evidence and theoretical models we've explored, it's crucial to understand that the idea of a full ocean boiling away event in Earth's deep past is not universally accepted within the scientific community. While certainly a fascinating and thought-provoking hypothesis, it represents one end of a spectrum of scientific opinion when it comes to explaining the peculiar geological and isotopic anomalies found in ancient rocks. The sheer scale of such an event makes it incredibly difficult to prove definitively, and researchers are constantly proposing alternative explanations that could account for the same observations without requiring complete vaporization of Earth's surface water. One prominent alternative hypothesis suggests that instead of total ocean obliteration, Earth experienced periods of extreme, episodic drying. Imagine vast stretches of the planet's surface becoming arid, with oceans shrinking dramatically and retreating into deeper basins, or even fragmenting into isolated hypersaline lakes. This could have been driven by prolonged droughts, sustained shifts in atmospheric circulation patterns, or even periods of enhanced subduction, where oceanic crust and its trapped water were rapidly pulled into the mantle. This scenario would still leave behind extensive evaporite deposits and desiccation cracks, and could certainly alter isotopic ratios in ancient minerals, but it doesn't necessitate the complete disappearance of liquid water from the planet's surface. The nuances in the geological record are subtle, and distinguishing between total loss and extreme desiccation requires incredibly precise analysis and careful interpretation. The challenge of reconstructing events from billions of years ago is immense. We're essentially trying to piece together a jigsaw puzzle with most of the pieces missing and no picture on the box. Scientists rely on incredibly minute chemical signatures, the arrangement of ancient rock layers, and sophisticated computer models to infer past conditions. Every new discovery, every refined analytical technique can shift the prevailing understanding. For example, some isotopic anomalies previously attributed to global boiling might, with further research, be explained by different temperature regimes in localized basins or by unique hydrothermal processes. The dynamic nature of scientific inquiry means that hypotheses are constantly being tested, refined, and sometimes even discarded as new data emerges. It's a continuous process of questioning, observing, and reinterpreting, driven by a collective effort to understand our planet's most enigmatic past. This ongoing debate isn't a sign of weakness in the science, but rather its strength, a testament to the rigorous, self-correcting nature of the scientific method as researchers strive for the most accurate and comprehensive picture of Earth's history. So how exactly are scientists able to peer back billions of years and even propose such a dramatic event as an ocean boiling away? The answer lies in remarkable technological advancements that have revolutionized our ability to analyze the most ancient relics of our planet. One of the most powerful tools in this endeavor is mass spectrometry, a technique that allows researchers to precisely measure the mass and abundance of individual atoms and molecules. When applied to ancient rock samples and minerals like the incredibly resilient zircons we discussed earlier, mass spectrometry can detect the most minute variations in isotopic ratios. For instance, the ratio of different oxygen isotopes, oxygen-16 versus oxygen-18, can act like a thermometer, revealing the temperature of the water from which a mineral crystallized. Subtle shifts in these ratios can tell geologists whether water was present, how hot it was, and even if it was liquid, vapor, or ice. Similarly, hydrogen isotopes, specifically the ratio of deuterium to hydrogen, offer crucial insights into the history of water itself, indicating whether it was lost to space or incorporated into the planet's interior. These aren't just crude measurements. Modern mass spectrometers are so sensitive they can identify variations smaller than parts per thousand, opening up a microscopic world of information about Earth's macro-scale past. Beyond analyzing existing samples, another critical advancement comes from high-pressure experimental petrology. Imagine trying to understand what happens deep inside the Earth, where pressures are immense and temperatures reach thousands of degrees. Scientists can now recreate these extreme conditions in specialized laboratories, using devices like multi-anvil presses or diamond anvil cells. They can squeeze tiny rock samples to pressures equivalent to those found hundreds of kilometers beneath our feet and heat them to volcanic temperatures. By doing so, they can observe how minerals behave, how water is incorporated into or released from their structures, and how rocks melt and crystallize under conditions relevant to early Earth. For example, understanding how much water different minerals can hold at mantle pressures helps inform the wet versus dry mantle debate and provides crucial data for models that track water cycling between the surface and deep interior. These experiments provide the fundamental laws of physics and chemistry that govern long-term geological processes, allowing scientists to interpret the ancient rock record with greater confidence. Finally, the increasing sophistication of computational modeling has become indispensable. With massive computing power, scientists can build complex digital simulations of Earth's early atmosphere, oceans, and interior. These models can incorporate all the physical and chemical laws derived from laboratory experiments and observed geological data, allowing researchers to test various hypotheses about past events. For instance, a computational model can simulate what would happen to Earth's atmosphere if a certain amount of greenhouse gases were released, or how an ocean might behave if surface temperatures rose beyond a critical threshold. They can run scenarios like a runaway greenhouse effect or a large-scale impact event and predict the resulting geological and isotopic signatures. By comparing these predictions with the actual evidence found in ancient rocks, scientists can refine their understanding and narrow down the possibilities for Earth's past. These cutting-edge technologies are not just providing answers, they are allowing scientists to ask entirely new questions, unlocking secrets of our planet's deep history that were once considered utterly unknowable, bridging the gap between subtle geochemical traces and continent-scale cataclysms. The possibility that Earth once lost its oceans, even if temporarily, fundamentally challenges our perceptions of a static, life-sustaining planet. It forces us to confront the immense power and indifference of geological forces, far beyond anything humanity has ever witnessed or could even conceive. We often view Earth as a stable home, a blue marble teeming with life, almost a given in the vastness of space. But the idea of an ocean boiling away shatters this comforting illusion, revealing a world that has endured cataclysms so profound they reshaped its very surface and atmosphere. This isn't just about rocks and water, it's about shifting our perspective from a familiar, constant habitat to a dynamic, evolving entity, capable of both immense destruction and incredible recovery. This unsettling thought also brings into sharp focus the inherent fragility of the conditions that allow life to flourish. Liquid water, a stable temperature range, a protective atmosphere, these are not guaranteed features of a planet. They are the result of a delicate, intricate balance that can be tipped by cosmic impacts, extreme volcanism, or runaway atmospheric feedback loops. The fact that life, in some form, persisted through or re-emerged after such a potential event speaks volumes about its incredible resilience. It suggests that life on Earth has a tenacity almost beyond comprehension, capable of adapting to conditions that would seem utterly inhospitable. This deepens our appreciation for the sheer improbable persistence of biological systems, pushing the boundaries of what we consider habitable. Furthermore, pondering a boiled-away ocean invites us to reflect on Earth's remarkable resilience. Despite these theoretical extremes, our planet eventually recovered, cooling, reaccumulating water, and allowing life to diversify into the astonishing array we see today. This recovery is not a passive process. It involves complex feedback mechanisms between the mantle, the crust, the oceans, and the atmosphere. It suggests a planetary system that, while capable of immense swings, also possesses an underlying stability that allows it to self-correct over geological timescales. This perspective moves us away from anthropocentric views where human actions are the sole drivers of change and places us within a grander narrative of planetary evolution where Earth itself is a powerful, active participant. Ultimately, the philosophical implications of an ocean that may have boiled away resonate deeply with our modern concerns about climate change and environmental stewardship. If Earth in its early history could undergo such a drastic transformation due to natural forces, it underscores how sensitive our planet's climate system truly is. It serves as a stark reminder that the balance maintaining habitability is indeed delicate. Understanding these ancient, extreme events isn't just about academic curiosity. It reshapes our perception of planetary vulnerability and the critical importance of maintaining the conditions that sustain complex life. It encourages us to view our planet not as an inexhaustible resource, but as a complex, vulnerable system that we are now, for the first time in its history, influencing on a geological scale. Shifting our focus from Earth's deep past to the cosmic frontier, the insights gained from contemplating a potentially boiled-away ocean on our own planet offer profound, perhaps even universal, lessons for astrobiology and the grand search for habitable exoplanets. The very concept of the Goldilocks Zone, that sweet spot around a star where temperatures are just right for liquid water to exist on a planet's surface, becomes far more complex when you consider Earth's own turbulent history. Our planet pushes the boundaries of this zone, showing that habitability isn't just about orbital distance. It's about a dynamic interplay of geological processes, atmospheric composition, and even the planet's internal heat engine over billions of years. When we envision alien worlds, we tend to project our current Earth onto them, a stable blue marble with vast oceans. But what if many potentially habitable exoplanets have endured, or are currently enduring, their own versions of extreme thermal events? Understanding Earth's thermal history, especially the possibility of a superheating event that vaporized its oceans, helps scientists refine their models for planetary evolution around other stars. It moves beyond a simplistic view of a planet simply being in or out of the Goldilocks zone. Instead, it prompts us to ask deeper questions. What is the geological activity like on that exoplanet? Does it have a strong magnetic field? What was its early atmospheric composition? The answers to these questions could mean the difference between a thriving water world and a barren, desiccated rock, even if both reside within their star's habitable zone. This broadened perspective means that the search for alien life becomes less about finding Earth copies and more about recognizing the diverse, and often extreme, pathways a planet can take while still potentially hosting life. This nuanced understanding fundamentally broadens our definition of planetary habitability. Perhaps a planet that appears barren today might have once harbored oceans or could potentially redevelop them in the distant future. Conversely, a planet that seems promising could be on the verge of a runaway greenhouse effect. These insights from Earth's ancient past encourage astrobiologists to consider time as a crucial dimension in habitability. A planet might be habitable for only certain billion-year windows, or it might experience cycles of extreme desiccation and recovery. This dynamic view of habitability makes the search for life elsewhere far more thrilling and complex. It means we might need to look for past signs of water, or even for life adapted to intermittent periods of extreme heat and dryness, rather than just seeking out perpetually temperate, ocean-covered worlds. Our own planetary history offers a dramatic case study in the fine line between persistent life and complete barrenness, reminding us that the story of habitability is rarely simple. From the chilling prospect of a vanished ocean to the enduring resilience of life, our journey through the ocean that boiled away evidence of Earth's most extreme superheating event reveals a planet far more dynamic and extreme than we often imagine. We've explored the isotopic whispers, the geological scars, and the scientific debates surrounding a time when Earth pushed the boundaries of habitability, reminding us that our blue marble has endured truly unimaginable trials. This grand narrative of planetary evolution, filled with cataclysms and recoveries, underscores the intricate dance between geology, atmosphere, and biology, offering profound insights into our planet's past and crucial lessons for its future. What other hidden extreme events in Earth's history await discovery, and how might they further reshape our understanding of life's incredible tenacity? Share your thoughts in the comments below, subscribe for more deep dives into historical mysteries, and let's continue unearthing the secrets of our astounding planet.